Right now, drifting through space, there spins a planet that challenges expectations. At its closest, Venus approaches Earth by just 38 million miles, nearly our twin in size and mass, yet transformed into a furnace where metal softens in sunlight and winds circle the globe faster than any hurricane on Earth. Through a telescope, Venus looks calm, soft white clouds wrapped around a gentle sphere, but beneath that brightness lies an atmosphere so dense it crushed early machines, and even the toughest landers lasted only hours. They seldom explained how the sister became a warning. Tonight, we explore the real Venus, perhaps once similar to our own world, but driven into extremes no human could endure. We'll drift through sulfuric clouds, across volcanic plains the size of continents, and revisit the final transmissions of probes that vanished under pressures equal to the deep ocean. Scientists continue to ask one question. What if Venus isn't just a dead world, but a glimpse of our future? If you enjoy journeys that change how you see the universe, please like and subscribe, and tell me where in the world you're listening from. Let's begin. How Venus disguises its true nature behind cloud layers that reflect more sunlight than any other planet. Venus is the brightest planetary object in our sky. Even city lights cannot drown it out. Through a telescope, the planet appears wrapped in smooth white, its surface hidden beneath clouds that bounce sunlight back into space. To the human eye, it looks harmless, almost gentle, but that brightness is a mask. Those cloud layers are not cotton or mist. They are a chemical shield that conceals everything beneath them, and what they hide is nothing like the world we know. When spacecraft first aimed their instruments toward Venus, scientists expected clarity. They thought penetrating the clouds would reveal continents and oceans, or at least something recognizable. Instead, every wavelength bounced back. The clouds absorbed the wrong colors, reflected others, and confused every sensor sent from Earth. The atmosphere was so thick and uniform that early astronomers assumed it might even be a global ocean of cloud, calm, thin, and tranquil. They were wrong on every level. Nothing about the atmosphere is calm. Nothing about it is thin. To understand Venus, you have to understand light. On Earth, light enters our atmosphere, interacts with oxygen, nitrogen, and water vapor, and much of it escapes back to space as heat. It is a healthy cycle. Venus interrupts that cycle at every stage. Its clouds are composed mostly of concentrated sulfuric acid droplets suspended in dense layers of carbon dioxide. Each layer behaves differently. Sunlight enters, is reflected, scattered, refracted, and trapped. Some wavelengths are bounced outward, giving the planet its milky, deceptive shine. Others are sealed below, where they heat the surface like a closed furnace. The strange thing is how effective this disguise is. Venus reflects nearly 3/4 of the sunlight that touches it. That makes it brighter than Earth, brighter than Mars, even brighter than Jupiter. Despite being much smaller, the planet is so reflective that many ancient cultures thought it was two separate stars, one appearing at dusk, another at dawn. They could not imagine a single object so brilliant that it ruled both horizons. Underneath the clouds, the story becomes far less elegant. Light that makes it past the reflective haze enters a lower atmosphere thick with carbon dioxide. Every photon struggles to escape. Instead of cooling the planet, the trapped energy heats it relentlessly. Even in the darkness of a Venusian night, the planet stays around 460 degrees Celsius, hotter than the surface of Mercury, which is closer to the Sun. There are no cool months, no gentle evenings. It is perpetual daytime heat sealed under a shroud. This shielding is not just visual, it is psychological. The brightness fools the brain into thinking the planet's surface might be beautiful. In reality, the clouds are hiding instability. Beneath them, volcanic plains stretch for thousands of miles. Mountains rise almost as tall as Everest. The ground is scarred by fractures and collapsed crust. With every new radar scan, scientists found that what the clouds hid was not serenity, but violence. When the first robotic probes descended through the atmosphere, their cameras showed darkness until the final seconds. Even at noon, the surface was dim, lit not by a blue sky, but by a glowing orange horizon. What the probes saw was nothing like the planet's appearance from space. There were no white clouds overhead, no reflective beauty, only a crushing sky and a world lit by scattered rays of radiation. The mirror above Venus is not decoration, it is a warning label. The clouds are a byproduct of chemistry pushed to extremes. They reflect light because the atmosphere below no longer allows it to escape. The planet is bright because the world beneath is trapped. Venus is a lesson written in sunlight. Not everything beautiful is safe, and not everything bright is alive. Beneath its luminous disguise waits the harshest environment in the solar system, a reminder that appearances can be the most dangerous form of deception. Why Venus spins backwards so slowly that its surface takes longer to rotate than it does to orbit the Sun. Venus rotates in a way that feels wrong. Its surface turns backward, opposite the direction of most planets, and it turns painfully slowly. One full Venusian day takes about 243 Earth days, yet the planet completes its orbit around the Sun in just 224. If you stood on its surface, assuming you could survive the heat, pressure, and toxic air, you would watch the Sun crawl across the sky in the reverse direction, rising in the west and setting in the east. The planet is locked in a slow-motion spin, and its reasons are anything but intuitive. The story begins with momentum. Planets form from rotating clouds of dust and gas. As gravity pulls material inward, the cloud spins faster, the same way a figure skater accelerates when pulling in their arms. Almost every world in our solar system inherited that direction. Venus did not. Something bent it out of alignment. Some scientists point to a colossal impact early in its history, a collision large enough to flip the planet's rotation. We see evidence of similar events elsewhere. Uranus, tilted almost sideways, and Earth, whose giant impact formed our moon. Venus may have been struck by a world-sized object that left it spinning backwards. Another explanation involves the planet's dense atmosphere. Venus is not just a rock with air around it. Its atmosphere acts like an enormous brake. The pressure at the surface reaches 92 bars, closer to the depth of an ocean trench than a sky. All that mass rubs against the planet as it rotates, slowing its spin over millions of years. The friction is subtle on any given day, but over geological time, small forces win. Winds, surface drag, tides created by solar heating, all of them work to resist rotation. Venus became a world slowed by its own weather. There is also sunlight itself. Solar radiation hits Venus unevenly, heating one hemisphere more than the other. This difference creates atmospheric tides, massive pressure waves that act like invisible gears, pushing against the planet's rotation. On Earth, atmospheric tides exist, but our rotation is strong enough to ignore them. On Venus, they matter. Researchers using models and radar tracking have shown that these thermal tides may be powerful enough to change the planet's day length by minutes each year. Imagine a world so sluggish that sunlight shifts its spin. The odd rotation affects everything else. Wind systems, storm patterns, and temperature gradients all move in an environment where the surface barely turns. The upper atmosphere does the opposite. It races. Clouds circle the planet every 4 days. While the ground crawls slowly beneath, the atmosphere sprints above it, creating a phenomenon called superrotation. This contrast is extreme. The planet's surface takes months to complete a rotation. The winds complete one in less than a week. It is like a treadmill where the air is sprinting and the world beneath barely walks. The slow spin also influences the planet's geology. On Earth, rotation and plate movement help distribute heat from the interior. Venus traps its heat. Without rapid rotation or tectonic plates, energy from the mantle accumulates. Periods of relative stability might stretch for millions of years, only to end in violent resurfacing events, massive outflows of lava that reset vast regions at once. A world that rotates too slowly cannot easily release internal stress. All of this leads to a planet that doesn't behave the way we expect. Venus looks like Earth's sibling, but its rotation reminds us it is something fundamentally different. A world that turns backward, slowed by atmosphere, sculpted by sunlight, and possibly scarred by ancient impacts. A planet where time itself feels broken. On Venus, the simplest question, how long is a day, doesn't have a simple answer. The planet forces us to rethink what a day even means. How the Venusian atmosphere reaches 92 bars, equal to the deep ocean, crushing landers in minutes. Venus does not crush you with mountains or storms, it crushes you with air. At the surface, the atmosphere reaches 92 bar of pressure, equivalent to standing nearly a kilometer beneath Earth's ocean. That number doesn't feel real until you imagine a spacecraft designed to survive the vacuum of space, suddenly being treated like a submarine. On Venus, the sky itself behaves like water. The deeper you descend, the heavier it becomes, until metal buckles and electronics fail under its weight. Understanding why begins at altitude. High above the clouds, Venus looks ordinary. The air is thin, temperatures are almost comfortable, and a probe can float as if it were drifting through Earth's upper atmosphere. But as soon as it begins to fall, the world changes. The gases thicken, carbon dioxide piles up layer by layer, each kilometer adding weight. Hydrogen and oxygen do not form the breathable air we know. Instead, sulfuric acid droplets drift in suspension, forming clouds that block most light, trapping heat like insulation. On Earth, air pressure at sea level feels gentle. We barely notice it because our bodies evolved inside it. Double that pressure and we feel it in our lungs. 10 times that and blood vessels begin to deform. On Venus, the pressure is more than 90 times greater. There is no adaptation that makes this survivable. There is no slow adjustment. Everything designed for spaceflight was built to endure near-vacuum conditions, not the crushing atmosphere of a planet that behaves like an ocean without water. When the Soviet Venera probes entered this environment, their descent was agonizing. Parachutes opened normally, sensors worked, cameras functioned, but as they moved downward, the atmosphere multiplied around them. Air resistance increased. The parachutes had to be cut early, not because the landers were falling too fast, but because the thick air slowed them so dramatically that descent nearly stalled. On Venus, terminal velocity does not mean plummeting. It means sinking, as if through a liquid. At around 50 kilometers, the air becomes dense enough to heat spacecraft just from friction. Electrical boards warm, external sensors overheat, and every meter closer to the surface compounds the force. Pressure squeezes each joint of the lander, forcing seals to the brink. When the Venera modules finally touched down, they lasted minutes. Some survived just long enough to send a few grainy images. Others melted or burst internally before they could transmit a single panorama. Unlike Earth, where air thins the higher you climb, Venus is layered like sediment. The planet is blanketed by carbon dioxide thousands of meters deep. Each layer presses on the one beneath it. Nothing moves freely. Even the wind cannot escape pressure. What seems like a gentle breeze at the surface is carrying forces equivalent to an underwater current. If you could stand there, every breath would feel like inhaling through concrete. And this is not simply a matter of bad weather or a chemical imbalance. Venus is stable in its brutality. The pressure does not fluctuate the way Earth's air pressure changes with storms or seasons. It sits there, constant, relentless, because the planet has no significant oceans to regulate temperature, no plate tectonics to break the surface, no global magnetic shield to disperse energy. Heat builds. Gas expands upward. Gravity holds it down. Over millions of years, the sky solidified into a crushing column. Scientists sometimes describe Venus as a world that drowned without water. The atmosphere became its ocean. Instead of waves and tides, there are shock layers and thermal gradients. Instead of storms, there are chemical mists and super-rotating winds. The surface sits beneath this ocean permanently, like a shipwreck resting on the seabed. This is why a suit cannot save you, not armor, not shielding. Even reinforced capsules designed for deep-sea research would fail. The Venusian sky does not merely sit above the ground, it presses against it. At 92 bar, the air is not weather, it is weight. A world where the sky itself becomes the enemy. The mechanics of the runaway greenhouse, trapped infrared radiation, and the planet's inability to cool. On Venus, heat enters the atmosphere easily. Sunlight streams through the upper layers, passes through acid clouds, and reaches the lower air and surface. But when that energy tries to leave, it is trapped. The planet attempts to radiate infrared heat back into space, and the carbon dioxide that fills the atmosphere absorbs it, forcing the energy downward again. The surface bakes, the air thickens, and every additional degree raises the rate of heat retention. The process is self-sustaining. Venus no longer cools. The key to understanding this begins with the chemical makeup of the air. Carbon dioxide is the dominant gas, nearly 96% of the atmosphere. On Earth, CO2 is measured in parts per million. On Venus, it is the air itself. Carbon dioxide molecules absorb infrared wavelengths efficiently. When sunlight hits rock or dust on the surface, that material warms and re-emits energy as infrared radiation. Instead of escaping, the heat is absorbed by surrounding gas molecules. They vibrate and collide, transferring energy downward. Each cycle increases the temperature at the surface. That heat does not rise naturally. Earth has oceans that pull heat downward and redistribute it, winds that lift warm air upwards, and a thinner atmosphere that eventually radiates thermal energy away. Venus has none of these safeguards. Its oceans evaporated long ago. Its winds move laterally, not vertically. The upper atmosphere simply reflects sunlight back outward, while the lower atmosphere traps every photon that makes it through. The result is a greenhouse effect so complete that even the dark side of the planet stays hot. Measurements from orbiting spacecraft show a thermal profile unlike anything found on Earth. At higher altitudes, temperatures fall sharply. But once you cross a certain threshold, the entire lower atmosphere becomes a uniform oven. Pressure compresses the gas, raising temperatures even further. The surface stabilizes not because it reaches equilibrium, but because there is nowhere left for the heat to go. The air is dense, the ground radiates constantly, and every molecule behaves like a miniature heater. The runaway greenhouse began long before the world became unrecognizable. Early in its history, Venus may have had water vapor in its atmosphere. Water vapor is an even more effective greenhouse gas than carbon dioxide. As sunlight struck the surface, oceans evaporated into the air, strengthening the greenhouse effect. The surface warmed. More water evaporated. The cycle accelerated. Eventually, the oceans turned to steam. Without liquid water to absorb heat, the planet entered a final phase: irreversible atmospheric saturation. When ultraviolet radiation from the sun split the steam molecules, hydrogen escaped into space. Oxygen reacted with rocks and sulfur compounds. The result was a surface stripped of oceans and an atmosphere dominated by carbon dioxide and sulfuric acid. Once water was gone, there was no mechanism to regulate temperature. Earth has evaporation, precipitation, weather cycles, and circulation. Venus has chemical feedback loops that only intensify heat. Even the ground contributes to the problem. Volcanic plains and basalt absorb sunlight well. Heated rock radiates strongly in infrared wavelengths, the exact frequencies that CO2 blocks. Every hour of daylight charges the planet like a battery. At night, it tries to discharge, but the atmosphere forces the energy back downward. The planet is locked in a cycle of heating without release. This is why the temperature remains stable around 460 degrees Celsius. Not because conditions balance comfortably, but because the atmosphere can no longer trap any more heat. It has reached saturation. Venus is not cooling, it is simply unable to get hotter. A runaway greenhouse is not a dramatic explosion. It is a slow, chemical trap. one that closes gradually until the planet beneath no longer remembers what cool air feels like. Sulfuric acid droplets that fill the upper atmosphere, and why every attempt to land beneath them fails. The clouds of Venus look soft and smooth, like blankets of mist, but they are not water vapor. They are aerosols of concentrated sulfuric acid suspended in layers tens of kilometers thick. These droplets begin in the upper atmosphere, where sunlight reacts with volcanic sulfur dioxide, forming particles that scatter light. From Earth, that scattering makes Venus appear pale and polished. Up close, it forms a chemical barrier that no aircraft or lander has ever passed through without suffering damage. To understand these clouds, you have to look at how they form. Venus has a constant supply of sulfur dioxide, released by volcanic eruptions and circulated upward through convection. When solar radiation interacts with it, the molecules break and recombine, forming sulfuric acid. The acid then condenses onto microscopic particles, creating hazes that merge into thick cloud decks. Each droplet reflects sunlight and absorbs heat, but also evaporates at lower altitudes, recycling back into gas and rising again. It is a continuous chemical cycle, not a weather pattern that changes with seasons. When spacecraft enter this region, the droplets do not simply fall on them like rain. They cling to surfaces, corrode metals, degrade sensors, and interfere with optics. Early probes attempted to measure the chemical composition of the atmosphere by capturing samples in aerosols. The results were shocking. Many instruments returned readings that suggested an environment closer to battery acid than air. Protective coatings dissolved. Lenses fogged. Even the radio systems degraded, their antennas etched by the active compounds they were designed to study. The descent profiles of Venus missions reveal this hostile environment clearly. Above 60 kilometers, temperatures are manageable and pressures are tolerable. Here, the air feels similar to Earth's lower stratosphere, cold, thin, survivable. But once a probe enters the cloud deck, the environment changes. The sulfuric acid droplets accumulate on exposed components, forming corrosive films. Winds shear the hardware, causing physical abrasion. The heat slowly rises, amplifying the chemical reactions. By the time a lander emerges from the bottom of the cloud layer, it is already damaged before it even reaches the crushing pressure below. Scientists once imagined flying aircraft through these clouds, balloons, gliders, or maybe powered drones. The problem is not lift. The atmosphere is dense enough to support flight. The problem is time. Even coated materials eventually break down when exposed to sulfuric acid at elevated temperatures. Every surface becomes vulnerable. Sensors that rely on optical clarity, batteries with metal contacts, even simple structural joints, all degrade faster than expected. These clouds also complicate communication. Radio waves weaken as they pass through charged droplets. Electrical discharges can occur when particles collide, producing faint, irregular flashes that mimic lightning. These events do not look like storms on Earth. They are slow electrical interactions in a thick medium, unpredictable and invisible to the eye. A lander transmitting upward must push its signal through layers that distort, absorb, or scatter it. Perhaps the most striking effect is psychological. When a probe sends its last images, they show a world dim and yellow, lit by scattered sunlight filtered through acid haze. There are no dramatic storm clouds or swirling systems, only a uniform mist that feels endless. It gives the impression of an atmosphere that is indifferent, neither raging nor calm, simply corrosive by nature. Earth's clouds can nourish, hydrate, or destroy. Venus's clouds only dismantle. They exist not as a meteorological system, but as a chemical shield built from volcanic output and solar energy. They hide the surface, distort data, and reject intrusion. For every mission that has tried to slip through them, the outcome has been the same. The clouds are never the place where the probe fails, but they always make sure the probe fails later. How winds at the cloud tops circle Venus in 4 days while the planet barely turns below. Superrotation. How winds at the cloud tops circle Venus in 4 days while the planet barely turns below. When scientists first measured the movement of Venus's clouds, they assumed the data was faulty. The planet takes 243 Earth days to rotate once, yet the winds several tens of kilometers above its surface complete a full trip around the planet in less than 4. The clouds move not slightly faster than the surface, but dozens of times faster, as if the atmosphere were trying to escape the body beneath it. To picture this, imagine standing on Venus's surface. The ground crawls under your feet, rotating in slow reverse. So slowly that you would wait months to see sunrise. Above you, hurricane-strength winds scream overhead, dragging entire cloud systems around the planet at hundreds of kilometers per hour. These are not localized storms, not temporary bursts. They are a global circulation pattern that has persisted for as long as we've observed the world. The cause is not simple. There isn't a single engine driving this atmospheric race. Instead, it is a chain of feedback loops. Sunlight strikes the upper clouds and heats them unevenly. Temperature differences create pressure gradients. The gradients accelerate the winds. The winds interact with the planet's rotation, transferring momentum through layers of air. Over time, these interactions amplify until the whole atmosphere moves like a conveyor belt wrapped around the world. One of the key players is something called thermal tides. When parts of the atmosphere warm during the day, they expand and rise. As they move, they generate waves, giant, planet-spanning oscillations that act like gears. These waves transport angular momentum toward the equator and upward, accelerating the air. On Earth, the effect is minor. On Venus, where the atmosphere is 90 times thicker, the effect compounds. Each wave pushes, each push adds speed, and the cycle repeats. Spacecraft sent to study Venus have confirmed how extreme this circulation is. The Japanese Akatsuki orbiter tracked cloud patterns at different heights. At the top of the clouds, around 70 kilometers, winds reached nearly 400 kilometers per hour. Deeper down, the speed slowed, but did not stop. Like a layered conveyor, the entire atmosphere rotates as one massive engine. Even at mid-altitudes, winds continue to accelerate, dragging the chemical haze across the globe. The lack of axial tilt adds another layer. Earth has seasons that shift heat between hemispheres. Venus barely tilts at all. Sunlight remains consistent, creating long-term stability in atmospheric motion. There is no seasonal reset, no winter calm. The energy balance becomes an endless loop of heating, circulation, and acceleration. Then there is friction, or rather, the absence of it. On Earth, surface features slow winds. Mountains, plains, forests, oceans, all interrupt airflow. Venus has no forests, no oceans, and its surface is buried beneath a crushing atmosphere. Winds do not mix with terrain, they glide above it. The planet's surface rotates so slowly that it offers almost no resistance. The atmosphere is free to outrun the ground indefinitely. The result is a two-layer world. The bottom is stagnant, hot, and heavy, an environment where movement is difficult and air flows like syrup. The top is dynamic and fast, a screaming band of motion constantly lapping the planet. This split alters everything: temperature distribution, chemistry, even the shape of the clouds. At the poles, giant swirling vortices form, rotating like massive gears that anchor the rest of the atmospheric system. We often think of weather as chaotic, storms that come and go, winds that shift. Venus challenges that assumption. Its atmosphere is not changing by the hour. It is a continuous machine. The surface may rotate slowly, but the sky never rests. If you could hover above the planet at cloud level, you would not see a world revolving underneath you. You would see the clouds themselves doing the rotating, dragging the entire atmosphere around a planet that barely turns at all. On Venus, wind is not a response to weather. Wind is the weather. How Magellan used synthetic aperture radar to map the surface through the clouds, revealing a fractured world. How Magellan used synthetic aperture radar to map the surface through the clouds, revealing a fractured world. For most of human history, Venus was a mystery sealed in brightness. Telescopes showed only an unbroken white disk, reflective and featureless. Every attempt to see beneath the clouds failed. Visible light bounced back. Infrared radiation scattered. Even ultraviolet imaging revealed only the swirling tops of storms. If Venus wanted to hide its surface, it succeeded, until the spacecraft called Magellan arrived. Launched in 1989, Magellan was not designed to photograph Venus in visible light. It didn't bother trying. Instead, it brought an instrument that could ignore the clouds entirely: synthetic aperture radar. Rather than capturing reflected sunlight, Magellan transmitted radio waves downward and measured how they bounced back. These signals penetrated the cloud layers and struck the surface. The returning echoes carried subtle differences: amplitude, timing, scattering angle. Like ripples in water, they revealed shape and texture. With those signals, Magellan built maps no telescope ever could. The method was deliberate. Venus's thick atmosphere is opaque to most wavelengths, but it is vulnerable to radar. Radio waves can slip through the haze, reflect off rock, and return to an orbiting receiver. A single pulse would be too weak to form an image. But Magellan didn't rely on single pulses. It fired thousands, then combined them mathematically, synthesizing, over time, the equivalent resolution of a much larger antenna. Not snapshots of the surface, but reconstructions. The first images were unlike anything scientists expected. Venus was not covered in oceans beneath the clouds. It was not lush. It was not smooth. Instead, the planet was scarred. Radar painted the surface in shades of brightness tied to reflectivity. Metallic minerals appeared bright. Lava plains appeared darker. Mountains cast radar shadows. Every pass revealed new shapes: long fractures, dome-like volcanoes, collapsed basins, ridges that stretched for hundreds of kilometers. Magellan proceeded systematically. Orbit after orbit, it mapped swaths of terrain until it had covered 98% of the planet. No other body besides Earth had been mapped with such detail. The data redefined our understanding of Venus. We learned that most of the surface was young, geologically speaking. Whole regions had been resurfaced by massive volcanic floods. Instead of weather-eroding mountains or water-carving valleys, Venus showed a history of catastrophic upheaval. The smooth basins detected by radar weren't seas. They were plains of cooled basalt, formed when magma once poured across the planet. The towering mountains weren't sculpted by uplift and erosion. They were pushed upward by internal pressures, then frozen in place. There were no riverbeds, no coastlines, no glaciers. The surface was dominated by features found nowhere else. Pancake domes created by slow, viscous lava. Coronae, enormous circular scars likely caused by mantle upwellings. And tesserae, complex ridged highlands that suggested intense deformation over unimaginable spans of time. Magellan revealed something else too. Venus is not static. Some volcanic structures showed signs of relative youth. Bright patches implied recent lava flows. Tiny shifts in surface emissivity hinted that the planet might still be active. The world under the clouds was not dead. It was simply inaccessible. The spacecraft's contributions did not end at imaging. It also measured gravity. As Magellan orbited, tiny changes in its velocity indicated how mass was distributed below. From those changes, scientists estimated crust thickness, mantle structure, and surface density. Some regions were unexpectedly heavy, suggesting buried mountains or mantle plumes. Others were strangely light, indicating empty cavities or deep fractures. Magellan's mission ended in a controlled crash. It was allowed to descend into the atmosphere and burn. Its final act was silence. Yet the data it collected remains one of the most detailed planetary surveys ever performed. Before Magellan, Venus was a bright circle in the sky. After Magellan, Venus became a map, harsh, fractured, and alien. Today, every conversation about Venus's geology begins with those radar echoes. Every future mission, Every hypothesis, every question about volcanism or tectonics traces back to one spacecraft that learned how to see through a planet's disguise. Magellan did not show us beauty. It showed us truth, a planet resurfaced by colossal eruptions, lava plains, shield volcanoes, and the evidence of recent activity. A planet resurfaced by colossal eruptions, lava plains, shield volcanoes, and the evidence of recent activity. Unlike Earth, Venus does not slowly recycle its crust through drifting tectonic plates and steady erosion. Instead, its surface appears to have been erased and rewritten in massive volcanic events. Magellan's radar images revealed plains that stretch for thousands of kilometers and show almost no signs of impact craters. That absence tells a story. Something covered the scars. Something melted the canvas. The most common features are broad basaltic plains formed by lava that once poured out like oceans without water. On Earth, lava spreads along fissures or through volcanic vents, cooling into rough fields or layered flows. On Venus, the flows seem to have been colossal. Entire regions are smooth and uniform, as if a planetary paint roller passed across the surface. Radar brightness indicates low relief, plateaus of frozen magma that extend uninterrupted for hundreds of miles. These plains do not show the delicate complexity of old landscapes. They show a reset. Then there are the shield volcanoes. They rise gently, not in towering cones, but in wide, shallow domes. They resemble the Hawaiian shield volcanoes on Earth, but on a scale that ignores familiar limits. Mart Mons, one of the largest, reaches more than 8 kilometers high. Its flanks slope gradually outward, suggesting repeated eruptions over long intervals. These giants are not isolated peaks. They sit embedded within volcanic provinces, regions where heat and pressure push upward through the crust. Radar also uncovered structures that do not exist on Earth. Pancake domes. They look as if blobs of viscous lava were squeezed out of the surface like dough. Their steep sides and flat tops suggest magma so thick that it barely flowed. Each dome stands alone, frozen in a shape that hints at intense internal pressure. Whatever forced that lava upward did not erupt explosively. It forced it out and let gravity settle the form. Even stranger are coronae, vast circular scars, often dozens or hundreds of kilometers across. These features resemble collapsed bubbles. Their edges are ridged or fractured, and the interiors show signs of uplift and deformation. The most supported explanation is internal upwelling. Hot mantle material rises, pushes against the crust, and then subsides. On Venus, with no plates, the force has nowhere to go. The crust stretches, breaks, and buckles in wide patterns before snapping back. All this points to a planet struggling to release heat. If Venus cannot bleed energy gradually, it stores it. The result may be catastrophic resurfacing events. Instead of thousands of small eruptions over millions of years, Venus may endure long periods of geological silence, followed by entire continents erupting at once. Some models propose that much of the surface was renewed within the past 300 to 600 million years. In planetary terms, that is yesterday. It implies that many older landscapes were buried under new rock like pages torn from history. And there may still be volcanic activity today. Venus Express detected variations in infrared emissivity, signatures that resemble cooling rock. Certain areas showed changes in the levels of atmospheric sulfur dioxide, a gas commonly released by eruptions. Magellan's radar revealed bright patches that could be geologically young lava flows. None of this is direct proof of ongoing activity, but it adds weight to a consistent pattern. Venus is not geologically dead. If you stood on the surface, you wouldn't see erupting lava fountains or ash clouds. You would see stability, a horizon of fractured terrain and gentle slopes. But beneath that stillness is a mantle that has nowhere to vent pressure. A world without tectonics is a pressure cooker. The crust locks in the heat, and when the buildup becomes too much, the release is not subtle. It is planetary. Venus is a volcanic world without respite. Not explosive, not dramatic, simply relentless. A planet that overwrites itself again and again, erasing its past each time pressure forces its molten interior into the light. The most complex terrain on Venus and why its formation suggests a violent geological past. The most complex terrain on Venus and why its formation suggests a violent geological past. In a world covered by lava plains and smooth volcanic blankets, there are areas that defy the pattern. These are the tesserae, vast regions of ridged, folded, and fractured highlands that rise above the surrounding landscape. They do not resemble cooled lava fields or simple mountain ranges. They look like continents that were bent, squeezed, and then frozen mid-collapse. Where most of Venus is young, tesserae may be ancient. They are scars the planet could not erase. Magellan's radar first revealed them in stark contrast to the surrounding plains. Tesserae scatter radar differently, producing bright and complex returns. Instead of uniform textures, they display intersecting grooves and plate-like segments. Their surfaces resemble cracked tiles, layered ridges, or warped slabs, hence their name, tessera, Latin for tile. They stretch across hundreds of thousands of square kilometers and reach elevations higher than many volcanic formations. If the lava plains are the smooth skin of Venus, the tesserae are the exposed bone. The key question is how they formed. Tesserae defy most simple geological explanations. Earth's continents deform through plate tectonics, folding, subduction, collision, but Venus has no global plate boundaries. There are no trenches, no continuous rifts across the surface. Whatever produced these patterns must have been different, possibly more intense. One theory is crustal compression. As the mantle pushed upward, the surface was forced to fold in multiple directions at once, producing cross-hatching that resembles crushed metal. Another possibility is that the crust softened temporarily, allowing it to wrinkle like a stretched sheet before stiffening once more. What makes tesserae especially puzzling is their relationship to elevation. They aren't simply fractured lowlands. They sit on topographic highs, often surrounded by volcanic plains that lie meters or kilometers lower. That suggests the tesserae existed first. They formed, rose, and then were encircled by later lava flows. The plains do not cut through them, they engulf them, which implies the tesserae survived resurfacing events that wiped out everything else. Some regions show evidence of extension, forces pulling the crust apart. Others show compression, forces pushing it together. Many display both. That combination hints at repeated cycles of geological stress. Venus may have gone through long periods where heat accumulated beneath the crust, lifting large blocks upward. When the pressure released, the surface sank, twisted, and fractured. Over and over, the crust stretched and compressed until it became a mosaic of broken plates without ever becoming true tectonic plates. There is also a chemical clue. Tesserae appear radar bright not only because of rough texture, but because of surface mineralogy. Some researchers think metallic minerals or weathered lava contribute to the reflectivity. Others suspect that tesserae have compositions unlike the surrounding plains, perhaps remnants of older, water-influenced rock that survived from a more temperate era. If Venus ever had shallow seas or a cooler atmosphere, these regions might be all that remains of those conditions. They would represent not only the planet's violent present, but a record of what Venus once was. When you compare tesserae to Earth's terrain, they resemble mountain belts and plateau systems, except without the clear plate motions that create them. They are the aftermath of a planet that cracked internally rather than colliding externally. In some places, ridges form checkerboard patterns. In others, radial fractures radiate out like spokes. Nothing about them is random. They are organized responses to pressures the planet could not distribute safely. Scientists have attempted to model the stresses required to create such patterns. The results are sobering. The crust would need to be thick, rigid, and subjected to forces strong enough to deform entire regions at once. These are not gentle geological processes. They are system-wide events, buried mantle plumes pushing upward, crust collapsing under its own weight, or global thermal changes that destabilize the entire lithosphere. Standing in a tessera, if survival were possible, you would see no rolling hills or smooth ridges. You would see sharp terrains, abrupt changes, and fractured ground stretching to the horizon. There would be no evidence of rivers, glaciers, or erosion. Only stress lines carved into rock. Tesserae are the skeleton of Venus that resurfacing could not bury. They are the memory of violence preserved in stone. Why Venus lacks plate tectonics, and what that means for heat buildup and catastrophic resurfacing. Why Venus lacks plate tectonics, and what that means for heat buildup and catastrophic resurfacing. On Earth, continents drift. Plates push and slide, fracture and subduct. The planet's crust is constantly recycled, lifted into mountains, dragged beneath oceans, broken by rifts, reshaped by collision. That movement spreads heat across the surface and funnels excess energy into the mantle's depths. Venus has none of that. Its crust behaves as a single rigid lid. No trenches swallow old crust. The energy from the interior has nowhere to go, so it accumulates. To understand why this matters, consider what plate tectonics actually does. It is not simply movement, it is a pressure valve. Every subduction zone on Earth is a drain where heat, minerals, and rock return to the mantle. Plate boundaries also allow new crust to form at mid-ocean ridges, spreading magma outward in controlled segments. This mechanism prevents heat buildup, regulates volcanism, and ensures that the continents do not sit motionless on the planet's surface. Now remove that mechanism. On Venus, the crust is locked. There are fractures, yes, tesserae, rifts, coronae, but they do not connect into a global system. Nothing cycles downward. Nothing is destroyed. The surface cannot be refreshed in steady increments. Instead, Venus accumulates thermal energy in its mantle over millions of years. Every volcanic eruption or mantle plume adds more heat to the system rather than relieving it. The planet becomes a sealed container. The consequences appear in the radar maps. Nearly 80% of Venus is covered in smooth volcanic plains. These plains are younger than one would expect for a planet that formed at the same time as Earth. Impact craters are sparse, and their distribution is nearly uniform. That uniformity is striking. It implies the surface did not erode gradually. It was reset. The most likely explanation is global, catastrophic resurfacing events. Not constant activity like Earth's volcanoes, but intervals in which enormous volumes of magma spilled outward across the planet, burying everything beneath. Imagine the crust behaving like a pressure cooker lid. Beneath it, heat builds. Mantle material warms, expands, and becomes buoyant. With no plates to relieve it, stress accumulates in the lithosphere. When it finally reaches a tipping point, the crust weakens in multiple regions at once. Volcanism erupts not as isolated flows, but as planet-wide flooding. Entire landscapes drown in molten basalt, mountains flatten, previous surfaces vanish. Geological memory is erased. There is indirect evidence of this cycle. Chemical measurements show sulfur dioxide levels fluctuating in the upper atmosphere over time. On Earth, volcanic activity releases sulfur dioxide, and declining levels after eruptions mark cooling. On Venus, spikes appear and fade without known storms or seasonal causes. These variations suggest bursts of volcanic output, perhaps modern ones, or echoes of recent events. Without plate tectonics, Venus also lacks the stabilizing feedback loops that keep Earth's climate habitable. On our planet, volcanic gases can eventually be absorbed by rock and ocean. Carbonates form. Carbon dioxide is locked away. On Venus, there are no oceans to dissolve atmospheric gases and no plate boundaries to bury them. Volcanic emissions accumulate. Carbon dioxide remains. Sulfurous compounds cycle through the atmosphere. The greenhouse intensifies with every eruption. The absence of tectonics explains another puzzle: why Venus's surface is so uniform in age. Instead of an old hemisphere and a young hemisphere, instead of zones of ancient crust preserved alongside new crust, the planet reads like a single chapter written in molten rock. Whatever existed before is gone. Some researchers suggest that Venus may periodically enter long, quiet phases, millions of years of relative inactivity, followed by sudden, planet-wide melting events. Others propose that the crust behaves semi-rigidly, flexing and bending under extreme heat without breaking into plates. Both theories point to the same reality. Venus cannot vent energy gradually. Earth breathes. Venus holds its breath. If geology is a planet's language, Earth speaks in constant movement. Venus speaks in silence, interrupted only by catastrophic bursts. What happened to Venus's water? Photodissociation, solar wind stripping, and the loss of hydrogen to space. What happened to Venus's water? Photodissociation, solar wind stripping, and the loss of hydrogen to space. If Venus ever had oceans, they did not simply evaporate. They disappeared. The planet's early atmosphere likely contained water vapor, just as Earth's did, but as the surface warmed, that vapor no longer condensed into rain. Instead, it formed dense layers high above the ground, exposed directly to the harsh ultraviolet radiation of the sun. That radiation split water molecules apart, tearing hydrogen away from oxygen. The lighter hydrogen escaped into space. The oxygen reacted with rock and sulfur compounds. Over millions of years, the oceans were not lifted. They were broken down and erased. To understand this process, imagine a planet trapped under a magnifying glass. On Earth, evaporated water rises and falls in cycles. Storms form, condensation occurs, rain returns to the sea. Venus could not cycle anything. Its atmosphere was already thick, and its surface grew hotter. Every gram of water that evaporated joined the greenhouse effect, increasing temperature, accelerating evaporation further. At a certain point, there was no liquid water left, only steam. This phase is called a runaway greenhouse. Once water vapor rose high enough, ultraviolet light did the rest. Hydrogen atoms, now separated from oxygen, had very little to hold them back. Venus has similar gravity to Earth, but hydrogen is the lightest element in the universe. Even a weak push can send it drifting upward, where it is swept away by the solar wind. That wind is a stream of charged particles flowing from the sun at hundreds of kilometers per second. Earth has a magnetic field that deflects it. Venus does not. The result is long-term atmospheric scouring. Spacecraft have measured the remnants of this process. Instruments detect hydrogen escaping from the upper atmosphere, streaming away like a faint tail. They also detect deuterium, hydrogen's heavier isotope, left behind at higher concentrations. Because deuterium is heavier, it escapes more slowly. The result is a ratio on Venus much higher than on Earth, a fingerprint that tells us how much normal hydrogen was lost. It is indirect evidence of oceans that are no longer there. This wasn't a sudden catastrophe. It took millions of years. Small changes in solar brightness amplified the greenhouse effect. Each increase in temperature allowed more water vapor to rise. As the upper atmosphere accumulated vapor, ultraviolet radiation reached deeper into it. Photodissociation increased. Hydrogen loss accelerated. The feedback loop was relentless. More heat, more vapor, more hydrogen stripped away. Once most hydrogen was gone, oxygen could not reform water. Instead, it bonded with basalt, iron, and sulfur. The planet's surface became chemically altered, oxidized, and hardened. Eventually, Venus settled into a new equilibrium. Not cooler, but hotter. Not wetter, but bone dry. The current atmosphere contains only trace amounts of water vapor, less than 1/100th of 1%. By planetary standards, that is desert-level dryness. The air is not only unbreathable, it is devoid of the molecules life depends on. This loss changed everything else. Without water, there was no mechanism to absorb carbon dioxide into minerals on a global scale. On Earth, oceans dissolve CO2 and store it in sediments, coral, and carbonate rocks. Venus lost that ability. Carbon dioxide remained in the atmosphere, building pressure and sealing heat. Sulfur dioxide from volcanic eruptions rose upward, forming acid clouds. The chemistry that might have stabilized the planet instead pushed it further into instability. Atmospheric escape continues today, but much slower. Most hydrogen is already gone. What remains is an atmosphere of CO2 and nitrogen, heavy and stagnant. The planet still interacts with the solar wind, forming an induced magnetosphere, a faint, comet-like bubble. But it protects nothing. The upper layers thin progressively, particles drift away, and the dry planet beneath remains unchanged. When we look at Venus, we do not see a world that simply overheated. We see a world that lost its water molecule by molecule until nothing was left to cool it. Not by evaporation. Not by evaporation. By destruction. Why sulfuric acid droplets evaporate before reaching the ground? Rain that never touches the surface. Why sulfuric acid droplets evaporate before reaching the ground? Rain that never touches the surface. The clouds on Venus produce droplets just as water clouds do on Earth, but the substance they form is sulfuric acid. High in the Venusian atmosphere, temperatures and pressures allow these droplets to condense and fall downward. For a brief moment, it resembles rain. But by the time the droplets descend into the lower layers, the environment changes. Temperatures rise sharply. The droplets do not hit the ground. They evaporate, turning back into vapor halfway through their descent. It is a planet where rain is permanent, but rainfall is impossible. To understand why, start with altitude. Between roughly 50 and 70 kilometers above the surface, Venus maintains a thin window of conditions that resemble what humans would consider survivable. Temperatures are below boiling. Pressure is similar to Earth's lower atmosphere. Here, sulfuric acid forms clouds just as water condenses at high altitude on our planet. Microscopic droplets collide, merge, and become larger. Gravity begins to pull them down. If you could drift inside these layers, it would feel humid and hazy, a corrosive mist hanging in the air. Descend just a few kilometers, and everything changes. The atmosphere thickens, pressure climbs, temperatures surge past the point where sulfuric acid can remain liquid. Instead of falling in sheets or droplets, the acid vaporizes. What began as raindrops becomes gas again, rising back toward cooler layers where condensation restarts. Each droplet is trapped in a cycle it can never complete. Form, fall, vanish, repeat. The planet's hydrological system is a loop of corrosion that never reaches the ground. This cycle matters because it defines the chemistry of the entire atmosphere. On Earth, rain washes particles from the air, transports minerals, erodes soil, and feeds rivers. On Venus, there is no cleansing process. Nothing falls to the surface and returns upward. The lower atmosphere remains stagnant, filled with carbon dioxide, nitrogen, and trace gases. The acid exists only in the middle layers, where it circulates endlessly. It never cools the surface. It never transfers heat away. It never dilutes the chemicals that build there. Spacecraft descending through these clouds reported the effects directly. Instruments showed droplets hitting external surfaces, then disappearing almost instantly. The probe was not warmed only by air. Heat radiated upward from the surface itself, forcing evaporation even before the lander reached the lower layers. Sensors that could sample droplets rarely survived long enough to do so. The acid etched metal frames, degraded coatings, and distorted camera lenses. Even a robust design could endure only a brief encounter with the environment. The droplets themselves are not like natural rainwater. Sulfuric acid forms when sulfur dioxide from volcanic output meets sunlight and trace oxygen. On Venus, this chemistry is constant. Instead of storm cells, there are long, banded layers of horizontally stretched clouds. They do not break apart into showers. They remain suspended, like corrosive fog. Their movement is driven by the planet's super-rotating winds, which carry them around the globe in days. From above, orbiters see streaks and patterns, filaments of acid, mist swirling where sunlight interacts with atmospheric currents. If a droplet somehow did survive long enough to reach the surface, it would not behave like water. The ground temperature would vaporize it instantly. The pressure would crush any container holding it. The chemical reactions with surface minerals would tear it apart. Venus's crust is not neutral. Basalts and metal-rich compounds react violently with acid, creating salts and gas products that travel upward again. The interaction between sky and stone is never gentle. When planetary scientists describe Venusian rainfall, they use terms that do not apply to Earth. It is not precipitation, it is recycling. The sulfuric acid is born in sunlight, condenses, attempts to fall, and is destroyed by heat. The lower atmosphere becomes a furnace that returns everything to gas. This is one of the clearest illustrations of how Venus diverged from Earth. Both planets have clouds, both once had chemistry shaped by water, but one world rains, nourishes, and cools. The other tries to rain and fails. On Venus, gravity pulls droplets downward, but physics rejects them. The sky never touches the surface. Rain exists only in theory. Venus's absent magnetic field and how direct exposure to the solar wind rewrites its upper atmosphere. Venus's absent magnetic field and how direct exposure to the solar wind rewrites its upper atmosphere. On Earth, a magnetic field reaches outward from the core, forming an invisible barrier that deflects charged particles from the sun. We live beneath a protective dome of magnetism that shields our atmosphere from erosion. Venus lacks that shield. It faces the solar wind directly. Every second, streams of energetic ions collide with the upper layers of its air, stripping atoms away and sculpting its atmosphere molecule by molecule. To understand why Venus has no magnetic field, you have to look inside it. Earth's field is generated by a dynamo, motion in a liquid iron core driven by rotation and convection. The core spins, currents flow, and magnetism emerges. Venus has a similar core composition, but its slow rotation cripples the process. A Venusian day lasts 243 Earth days. With so little spin, the molten iron inside does not churn the way it does inside Earth. Without rapid movement, the dynamo never forms. The planet is electrically quiet. Instead of a shield, Venus has an induced magnetosphere. The solar wind crashes into its upper atmosphere and bends around it, forming a weak envelope. But this bubble is reactive, not defensive. It grows and shrinks depending on solar conditions, offering inconsistent protection. Charged particles slip through. They collide with atoms of oxygen, nitrogen, and carbon dioxide. Some atoms are energized and flung upward, others break apart. The atmosphere slowly leaks into space. Spacecraft have measured this escape directly. When Venus Express orbited the planet, it detected streams of ions flowing away from the night side, like a comet's tail. Hydrogen and oxygen atoms drift outward, carried by magnetic interactions. Hydrogen escapes more easily because of its low mass. Oxygen, heavier and slower, lingers longer, bonding with surface materials or recombining into compounds. The process does not empty the atmosphere, but it rewrites it. The balance of gases changes over time. Without a magnetic shield, solar storms hit Venus with full force. Coronal mass ejections, giant eruptions from the sun, can compress its induced magnetosphere and hammer the planet with charged particles. These storms energize atmospheric atoms even more aggressively, accelerating loss. On Earth, such events cause auroras. On Venus, they strip away atmosphere and inject energy into layers already strained by heat. The consequences reach deeper than many realize. A weak or absent magnetic field influences not just atmospheric chemistry, but climate and habitability. On Earth, our oceans and continents evolved in a protected environment. The molecules that built life were not constantly torn apart by solar radiation. On Venus, any ancient oceans would have been exposed. As the planet warmed, water vapor rose to the upper atmosphere, where ultraviolet light split it apart. Without a shield, the solar wind carried hydrogen away into space. Venus lost the primary ingredient needed to moderate temperature. Once that escape began, there was no reversal. The environment that remains reflects this long battle. The upper atmosphere of Venus forms ionized layers where solar particles collide with gas. The ionosphere is chaotic, densities fluctuate, chemistry reacts constantly, and particles circulate upward and outward. It is a battlefield of energy, not a stable environment. Even the planet's backside, shielded from direct sunlight, shows trailing streams of ionized gases drifting away into space. Scientists think Venus once may have had a magnetic field early in its history. If the core was hotter or rotating faster, the dynamo could have been active. That window may have lasted only a short time. Once heat distribution and internal motion changed, the field shut down. Without a shield, erosion began. What started as a slow atmospheric leak eventually became a defining feature of the planet. We tend to imagine danger on Venus at the surface. Melting heat, crushing pressure, toxic clouds. But the deepest wound comes from above. With no magnetosphere to guard it, Venus stands exposed to the sun, stripped across billions of years. The atmosphere we see today is not just the result of chemistry and lava. It is the product of a planet left defenseless in the solar wind. The Soviet missions that touched down, melted, broke, and still changed everything we know. The Soviet missions that touched down, melted, broke, and still changed everything we know. In the 1960s, when humanity was racing toward the moon, a small group of engineers in the Soviet Union aimed at a different target. Their goal was not a flag, not a landing site, not human footprints. Their target was Venus, a world no one had seen beneath the clouds. They wanted to land on a planet whose atmosphere crushed metal. It was an ambition bordering on impossible. And still, they tried. The first attempts did not even reach the surface. Venera 1 lost contact during its journey. Later probes entered orbit or burned up as they descended. The atmosphere was far thicker than expected. Parachute systems designed for Earth-like conditions acted like anchors, slowing descent so dramatically that heat and pressure destroyed the spacecraft before they were near the ground. Engineers redesigned every part: the shape of the capsule, the thickness of the hull, the operating temperature of instruments. The duration batteries could last in an environment that would melt solder. The breakthrough came with Venera 7. In 1970, it became the first spacecraft ever to touch another planet's surface and transmit data from it. The landing was rough. The probe hit the ground at an angle and partially collapsed, but it survived long enough to send back numbers, not images, not panoramas, only readings. A temperature near 470 degrees Celsius, a pressure over 90 bars. Those two values changed everything. They confirmed a world that no lander could endure for long. The missions that followed grew bolder. Venera 9 and 10 in 1975 were the first to return images from the surface. The photographs were grainy, distorted, monochrome, but they showed something profound: fractured slabs of rock, boulders sitting on a lifeless plain, and a horizon under a thick yellow haze. There was no ocean, no vegetation, no terrain softened by rain or wind. The ground looked as if it had shattered and been left unchanged for eons. The wind was still. The air was heavy. The most advanced landers, Venera 13 and 14, arrived in the early 1980s. Their descent capsules were engineered like pressure vessels. Thick titanium shells, internal insulation, ceramic coatings. They were expected to last 30 minutes. They survived more than 2 hours. Venera 13 recorded sound, wind buffeting the microphone like a slow, distant roar. It analyzed soil, measuring elements in the rock. It photographed its surroundings with color cameras. The result was a view of a planet that looked almost familiar, but hostile in every way. Orange light, cracked ground, no horizon beyond the haze. Each mission revealed a little more. The landers confirmed volcanic rock, likely basalt. They measured slow winds at the surface, nothing like the atmospheric superrotation above. They detected a chemical environment toxic to both metal and electronics. Even insulated components degraded quickly. Gaskets softened. Sensors overheated. Internal temperatures rose despite elaborate cooling systems. Every probe died silently, not because of failure, but because physics had reached a limit. The Soviets understood this. They knew no lander would remain active for days or weeks. The mission plan was simple: survive long enough to transmit. Instruments were designed to work immediately after landing, with no warm-up, no calibration period. Some devices operated only once. They crushed samples or fired detectors the moment the lander touched rock. Everything was done in the first minutes, because there might not be a second. The Venera program did not conquer Venus. It did something more important. Those final transmissions, temperature readings, pressure values, photographs of broken stones beneath a sulfur sky, forced scientists to confront a planet far more extreme than theory had suggested. Venus was not Earth's failed twin. It was a world that had evolved into its own form of hell, not by chance, but by physics, chemistry, and time. No spacecraft since has survived on the surface longer than Venera. Modern missions circle above, watching from orbit. The ground remains as the Soviets found it. Hostile, crushing, and silent. The Veneras burned, melted, and fell apart, but they changed everything we know. The temperate band 50 to 60 kilometers above the surface, where pressure and temperature resemble Earth. The temperate band 50 to 60 kilometers above the surface, where pressure and temperature resemble Earth. In that narrow slice of Venusian atmosphere, conditions shift from impossible to strangely familiar. Temperatures fall to around 20 to 30 degrees Celsius. Pressure drops to about 1 bar, close to sea level on Earth. The air becomes less like molten metal and more like the air inside a pressurized cabin. For a moment, the planet seems to pretend it is livable. It is the closest Venus comes to mercy, a balcony above hell. This region is often called the habitable cloud layer, not because humans could stand outside and breathe, but because physics there stops trying to crush you. The corrosive compounds remain, and the winds still race around the planet, but the atmosphere is no longer lethal in seconds. The air density becomes manageable. A human wearing the proper protective suit could survive here far longer than they ever could at the surface. NASA engineers once examined this zone and asked an audacious question. What if exploration didn't mean landing? What if it meant floating? The density of the Venusian atmosphere allows lighter-than aircraft to remain buoyant. Balloons, airships, or even platforms could hang in the temperate band, drifting above the planet like silent observers. 2 probes released helium balloons that floated at roughly 54 kilometers. They lasted 2 days, collecting data on winds, temperatures, and pressure. The planet did not crush them. It simply carried them around the globe. The environment at these heights is not calm, but it is predictable. Winds flow eastward at hundreds of kilometers per hour, the same superrotation that dominates the upper atmosphere. A balloon released here would not hover in place. It would be carried around the planet every few days, tracing the same path non-stop. From orbit, these balloons would look like beads in a conveyor belt, moving, circling, never resting. Even with tolerable temperatures, there are hazards. The sunlight is filtered through clouds, turning the skies a pale, diffuse yellow. No blue horizon, no stars. The entire world is permanently overcast. The air is rich in carbon dioxide, baked with trace sulfur dioxide, and sprinkled with microscopic acid droplets. Any surface exposed to the air would corrode slowly. Sensors would need shielding, air intakes would need filtration. The environment is not deadly in seconds, but it degrades anything that lingers. Still, this layer fascinates scientists because it offers a paradox. Venus is a furnace on the surface, yet at this single altitude, conditions resemble Earth more closely than Mars does. Mars is cold, airless, and unforgiving. Hypothetical missions have imagined floating stations, crew capsules tethered beneath helium blimps, drifting endlessly, sampling clouds, and using solar panels to power instruments. They would never land. They would exist in a permanent twilight, collecting data from above a world that rejects everything below. Some even speculate about microbial life, not organisms crawling on rock, but particles suspended in droplets. If life existed on Venus, it would have vanished from the surface long ago. But this middle layer offers liquid phase chemistry, sunlight, and temperatures suitable for metabolic reactions. It is speculation, not evidence. Observations have found unusual chemical signatures, including possible phosphine, but none prove biology. Still, the question persists. If life adapts anywhere, would it adapt here? Above this band, temperatures fall further and pressure drops, eventually resembling the upper atmosphere of Earth. Below it, conditions deteriorate rapidly. Heat increases, pressure climbs, the air grows heavy and violent. At 40 kilometers, survival becomes impossible. At 20, the atmosphere becomes crushing. At the surface, everything breaks. The temperate layer is not a refuge. It is a brief interruption, an accidental balance created by physics. A small altitude where the world pauses between the furnace below and the corrosive winds above. A balcony in a burning building, not an escape. Venus offers that window for only one reason. The atmosphere is deep. On Earth, the zone of comfort is on the ground. The claimed detection, the controversy, and what it revealed about searching for life in hostile worlds. The claimed detection, the controversy, and what it revealed about searching for life in hostile worlds. In 2020, a team of astronomers announced something unexpected: traces of phosphine gas in Venus's atmosphere. On Earth, phosphine is associated with living systems or industrial processes. It is not produced easily by normal chemistry. The signal came from cloud layers in the temperate band above the surface, the only region of Venus where temperatures and pressures resemble anything close to Earth-like conditions. If the result was correct, it suggested something extraordinary. Chemistry that didn't fit the rules we understood, or perhaps hints of microbial life. The scientific world reacted in two ways: excitement and doubt. Excitement because phosphine is a biosignature on Earth. Doubt because Venus is a planet where nearly every known mechanism destroys biological material. The researchers used data from ground-based telescopes, detecting spectral signatures of the molecule. A peak in a narrow wavelength suggested phosphine was present in parts per billion. Not a lot, but enough to matter. In an atmosphere dominated by sulfuric acid and carbon dioxide, the existence of any phosphine would imply an unknown process. Almost immediately, other scientists challenged the result. Spectral detection is delicate. Clouds, temperature gradients, and instrumental noise can mimic signals. Venus is especially difficult to study from Earth because its brightness washes out weaker lines. Some argued that the spectral feature was misinterpreted, that sulfur dioxide, a common atmospheric gas on Venus, could produce a similar pattern. Others claimed the analysis methods overcorrected background noise. The response was not hostile, it was methodical. Teams reprocessed the same telescope data. Others used independent instruments to search for the same line. Results varied. Some saw nothing, some saw faint traces, some saw phosphine only in specific altitudes. The original authors refined their methods, lowered their estimates, and adjusted the model. 2. What exactly are we looking at? To understand why phosphine matters, you need to understand its chemistry. On Earth, the molecule is unstable in oxygen-rich environments. It breaks apart quickly unless continually produced. Anaerobic bacteria create it in swamps and sediments. Industrial routes make it in specialized reactors under high temperatures. In space, it is found in gas giants like Jupiter and Saturn, formed under extreme pressures and chemical conditions. But Venus has neither the deep atmospheres of gas giants nor the biological ecosystems of Earth. If phosphine existed there, it would require a mechanism we do not fully understand. One proposal was volcanic activity. Could eruptions generate the gas? Models showed that even extreme volcanic output would produce phosphine too slowly to match the detection. Another theory involved lightning or meteoritic delivery. Both options failed to explain sustained levels. A third possibility was photochemistry, light-driven reactions in the upper clouds, but known chemical pathways destroy phosphine faster than they create it. If it exists, something is replenishing it. But something does not have to mean life. The phosphine debate revealed a larger truth. Our understanding of Venusian chemistry is incomplete. The atmosphere is layered, turbulent, and filled with compounds that behave differently under high pressure and temperature. Reaction pathways that seem impossible on Earth may operate efficiently in the clouds of Venus. Solving that puzzle requires not assumptions, but measurements. This is why the phosphine announcement mattered, even if the detection proves incorrect. It forced scientists to re-examine Venus, a planet long dismissed as sterile. It demanded better instruments, modern missions, and new observations. It reminded researchers that seeking life cannot focus only on friendly worlds. It has to confront hostile ones, worlds that burned, worlds that dried, worlds that shattered. Because life, if it ever existed beyond Earth, might have adapted to environments that seem unreasonable to us. The phosphine debate is unfinished. New spacecraft will revisit the planet in the coming decade. Orbital probes will study cloud chemistry. Descent vehicles may sample droplets directly. The answer may be mundane. It may be revolutionary. It may be something we have not imagined. The signal was not a discovery of life. It was an invitation to ask a better question in a place where science once stopped looking. Earth and Venus as planetary siblings. How identical beginnings diverged into opposite outcomes. Earth and Venus as planetary siblings. How identical beginnings diverged into opposite outcomes. Both planets formed from the same cloud of dust and rock that surrounded the young sun. They accreted at nearly the same time, pulled together by gravity, fed by the same reservoirs of metals, silicates, and volatiles. Their diameters are nearly identical. Their densities differ by a fraction. They orbit the sun close enough that astronomers call them neighbors. In the early solar system, they were planetary twins, equal in mass, equal in promise, and born with the same potential to host oceans and atmospheres. When we imagine Earth's first billion years, we picture intense impacts, molten crust, oceans forming, and atmospheric change driven by volcanic gas. Venus likely experienced the same sequence. It probably had liquid water. It may have had shallow seas. For a while, the two worlds followed parallel paths. Neither planet was destined to become what it is now. Small differences, accumulating over time, determined their fates. One of those differences was distance. Venus orbits about 30% closer to the Sun. That distance does not sound like much, but in planetary climate, a few percent is everything. Venus received more sunlight than Earth from the very beginning. Slightly warmer oceans evaporated more readily. Water vapor, one of the most powerful greenhouse gases, entered the atmosphere in larger quantities. The warming intensified. More vapor rose. The cycle continued. Earth, by contrast, formed at a slightly cooler point. Liquid oceans condensed and stabilized early. Rain fell. Atmospheres cycled. Carbon dioxide dissolved into water. Minerals formed carbonates. A climate feedback loop emerged, one that allowed Earth to maintain temperatures within a narrow band despite fluctuations in solar energy. Venus never reached that equilibrium. Its water moved upward faster than it could be returned downward. Then came atmospheric chemistry. On Earth, ultraviolet radiation breaks apart water molecules, but the hydrogen does not escape easily. The magnetic field repels charged particles, protecting the upper atmosphere. Venus had no such barrier. Hydrogen, the lightest element, drifted away into space. Oxygen bonded with surface minerals, building a rusted crust. Over millions of years, the oceans vanished, not because they boiled away and fell again, but because the planet physically lost them. What began as weather became irreversible atmospheric escape. With water gone, the two worlds truly split. Earth continued to host oceans that moderated temperature and absorbed gases. Venus was left with carbon dioxide in overwhelming quantities. Without plate tectonics or oceans to store it, the gas accumulated layer upon layer. The greenhouse effect intensified. The atmosphere thickened. Temperatures soared. The cooling pathways Earth relied on simply didn't exist there. Rotation sealed their destinies further. Earth spins quickly, distributing heat around the globe. Venus rotates so slowly that its day is longer than its year. Heat lingers. Daylight lasts for months. Night brings no relief. The upper atmosphere rotates rapidly, but the ground beneath barely moves. This imbalance magnifies everything. Winds scream above, stagnation suffocates below, and no part of the planet cools enough to break the cycle. The geology followed the climate. Earth's crust fractured into plates that subduct, recycle, and refresh the surface. Mountains rise, continents drift, and ocean floors renew. Venus's crust never broke into global plates. It hardened as a single shell, without a mechanism to release heat gradually. Pressure built over time until enormous volcanic events resurfaced everything. Earth's history is recorded in layers. Venus's history is erased in sheets of basalt. Looking at the two planets today, one might assume their differences were inevitable. They weren't. They emerged from small variations compounded across billions of years. Venus was not born as a cautionary tale. It evolved into one. Earth was not destined for habitability. It earned it through delicate balances that could easily have tipped another way. The most humbling truth is not that the two worlds diverged. It is how close they started. The same chemistry, the same ingredients, the same origin. One world became blue, alive, and dynamic. The other became sealed, hostile, and silent. There was never a dramatic moment when Venus failed. No instant catastrophe. Just tiny imbalances repeated endlessly, until one twin was no longer recognizable. Models of early Venus, possible shallow seas, and the moment evaporation became irreversible catastrophe. Models of early Venus, possible shallow seas, and the moment evaporation became irreversible catastrophe. When scientists simulate the young Venus, they do not imagine a desert of basalt or a furnace sealed under sulfur clouds. They imagine shallow water, scattered lakes, or even oceans blanketing lowlands. Not deep blue seas like Earth's, but warm surface water, thin layers that might have cooled the crust, moderated temperatures, and allowed the first atmosphere to stabilize. For a period of hundreds of millions of years, Venus may have been wet. The evidence for this lies in isotopes. Hydrogen on Venus exists in two forms: normal hydrogen and a heavier variant called deuterium. Lighter hydrogen escapes into space more easily. Heavy hydrogen lingers. Venus has a ratio far higher than Earth's, an echo of oceans that once evaporated and lost their hydrogen to space. It tells us something violent happened, but not in a single disastrous moment. It unfolded slowly, invisibly, like a climate experiment left running without supervision. In the early days, the sun was dimmer than it is now. Both Earth and Venus received less radiation. Earth stabilized. Venus began in the same direction, but its orbit placed it closer to the sun, close enough that surface temperatures were slightly higher. That small difference changed everything. Lakes evaporated more easily. Shallow seas produced more water vapor. And water vapor is an efficient greenhouse gas. It trapped heat in the atmosphere, warmed the surface, and fed the cycle further. This process is called a positive feedback loop. Warm air holds more moisture. More moisture traps more heat. More heat accelerates evaporation. If a planet has oceans deep enough to moderate the cycle, equilibrium eventually forms. On Earth, rainfall, ocean sinks, and carbonate formation pulled carbon dioxide downward. Venus had none of those safety nets. Water vapor accumulated and never condensed back into stable seas. At some point, Scientists debate exactly when Venus crossed a threshold. The oceans stopped behaving like liquids and became dense blankets of steam. Temperatures rose above the boiling point of water permanently. The surface could no longer cool enough at night or through seasonal cycles. It reached a state where no rain fell, no clouds condensed into droplets. Instead, all moisture found its way upward. Once in the upper atmosphere, ultraviolet radiation from the sun broke apart water molecules, severing hydrogen from oxygen. The hydrogen escaped into space. The oxygen reacted with basalt and volcanic minerals, forming oxides in the crust. What had been oceans became chemical residues. Venus did not lose its water to space in one dramatic event. It lost it molecule by molecule. Planetary scientists refer to this condition as a moist greenhouse. It is the step before total atmospheric collapse. During this stage, a planet still has liquid water, but slowly bleeds its oceans upward. Eventually, the process becomes irreversible. Venus reached that point and moved beyond it. When the last water was gone, the cycle did not reverse. It accelerated. Carbon dioxide dominated the atmosphere. Infrared radiation became trapped. The runaway greenhouse began. Had Venus cooled earlier, it might have stabilized. If clouds formed high enough to reflect sunlight before the planet became too hot, the world might have remained temperate. Atmospheric models suggest that if Venus had oceans deeper than 300 meters, they might have survived. But shallow seas evaporated too easily. The planet crossed a point where evaporation outpaced cooling, and there was no return path. This loss of water reshaped everything that came after. Without oceans, no carbonate cycle existed to bury carbon dioxide in rocks. Without rainfall, no erosion carved channels or valleys. Without liquid reservoirs, no slow climates emerged. The rocks hardened, the air thickened, the surface stopped evolving gently and instead reset catastrophically through volcanic floods. The ocean that never lasted is a ghost in the atmosphere. It exists only in isotope ratios, in computer simulations, and in the brief, fragile possibilities of a young planet that almost followed Earth's path. Almost, but not quite. A few million kilometers and a difference in solar exposure turned potential seas into steam and hope into heat. Theories behind atmospheric momentum transfer and strange wave structures that accelerate the clouds. Theories behind atmospheric momentum transfer and strange wave structures that accelerate the clouds. When scientists discovered that Venus's clouds circled the planet in only 4 Earth days, while the surface needed 243 to make a full rotation, they struggled to explain it. Venus does not turn fast enough to fling its atmosphere forward. Yet from the cloud tops, it appears as though the atmosphere itself has chosen a different rotational speed. The upper winds run laps around the world, while the planet beneath barely moves. This phenomenon is called superrotation, and it breaks nearly every rule we associate with atmospheric flow. On Earth, winds are shaped by rotation, terrain, temperature gradients, and day-night cycles. No wind system crosses the globe in a continuous band. Venus, however, behaves like a conveyor belt. Instead of circulating water vapor or storm fronts, the entire atmosphere becomes a single, connected engine. One that moves faster than the planet that hosts it. The origins of this engine likely begin with sunlight. Venus's thick atmosphere absorbs energy unevenly, creating large thermal contrasts between the day and night sides. Those contrasts generate pressure waves, massive atmospheric tides that push and pull on the air. Each wave transfers small amounts of angular momentum. Individually, one wave would do nothing, but Venus has billions of them, forming constantly, reflecting off cloud layers, and interacting with the lower atmosphere. Over time, these waves accelerate the circulation until the clouds outrun the surface. Another key is the lack of friction. On Earth, mountains block wind, oceans absorb heat, and the planet's surface continually exchanges energy with the atmosphere. Venus is different. Its terrain sits beneath a heavy, sluggish lower atmosphere with almost no interaction at cloud height. The upper layers slide over the lower ones like ice atop water. No landform slows the winds. No coastline redirects them. The environment above the clouds has room to accelerate freely. Spacecraft have seen evidence of this in real time. The Japanese Akatsuki orbiter, positioned in a high elliptical orbit, captured images of wave structures stretching thousands of kilometers. Some were shaped like giant bows or rippling curtains. One stood still over the mountains of Aphrodite Terra, a stationary wave anchored to surface topography below. Like a flag pinned in place by wind, it did not move while the surrounding atmosphere raced around it. This wave is thought to form when high terrain disturbs the lower atmosphere, sending energy upward until it slams into the cloud deck. Instead of dissipating, the wave remains suspended, pumping momentum sideways. There are also planetary-scale waves, Kelvin and Rossby waves, that travel around Venus and help maintain the superrotation. They act like gears in a transmission system. One set pushes energy toward the equator, while another pulls it toward the poles. Together, they couple the atmosphere into a single rotating layer. Where Earth's circulation is broken into cells and jet streams, Venus's is unified. The slow rotation of the planet itself amplifies the effect. Because Venus barely turns, the usual Coriolis forces that shape weather on Earth are weak. Instead of splitting winds into organized belts, Venus allows winds to merge into a single band. What begins as local circulation becomes global. Over millions of years, the atmosphere found its own rhythm, one that ignores the planet beneath. Yet despite decades of study, the mechanism behind superrotation is still not fully understood. Simulations reproduce parts of the pattern, but not all of it. Some models suggest that the lower atmosphere acts as a reservoir of hidden energy. Others suggest that turbulence feeds the circulation, injecting momentum at small scales that accumulates at large ones. New data from orbiters show that chemical composition may also play a role. Different gases absorb sunlight differently, leading to differential heating and unexpected wind behavior. What is certain is this: Venus is not a calm world hidden under its clouds. It is a spinning lens of atmosphere wrapped around a static surface. A planet where the sky never rests and the air itself runs faster than the ground. On Earth, you travel the world by walking across continents. On Venus, you could travel the world by letting the wind carry you. 4 days to circumnavigate an entire planet. Why Venus reflects so much light yet keeps almost all of the heat. Albedo versus thermal absorption. Why Venus reflects so much light yet keeps almost all of the heat. Albedo versus thermal absorption. From Earth, Venus looks bright, almost brilliant. It outshines every planet in the night sky, glowing like a polished mirror. That brightness comes from its albedo, the fraction of incoming sunlight it reflects. Venus reflects more than 70% of the sunlight that hits it, a value higher than snow-covered Earth or icy moons. If reflectivity alone determined climate, Venus should be cold. Instead, its surface is hotter than a furnace. The paradox is simple. Venus blocks visible light and traps infrared. The uppermost clouds are the key. They scatter visible wavelengths so efficiently that the planet becomes a beacon. Telescopes see only the sunlight bouncing off sulfuric acid droplets and thick haze layers. What they don't see is the much smaller fraction of sunlight that does penetrate. That fraction might be only a sliver of the incoming energy, but once it reaches the surface and warms it, the planet holds onto that heat with ruthless efficiency. When sunlight strikes rock or soil, the surface re-emits energy as infrared radiation, a wavelength invisible to the human eye. On Earth, that thermal radiation escapes into space or is partially absorbed and re-radiated until it eventually finds its way out of the atmosphere. Venus blocks this escape route almost completely. Carbon dioxide, which makes up most of its atmosphere, absorbs infrared frequencies remarkably well. Instead of passing upward, the radiation is captured, converted into molecular motion, and trapped. Every interaction reheats the air. The atmosphere is so dense that even a small amount of absorbed energy becomes overwhelming. A single cubic meter of surface air on Venus contains more mass than an entire room full of air on Earth. When those molecules vibrate with heat, the effect is amplified across billions of tons of gas layered from ground to cloud. The result is a greenhouse process that is not gradual, it saturates. Earth provides a useful comparison. Our planet reflects far less light, but the air is thin enough for heat to leak away. Venus reverses this advantage. It reflects almost everything, but the tiny fraction of solar energy that penetrates becomes permanently trapped. Imagine a solar oven wrapped in a mirror. Most energy bounces off, but the heat that slips through cannot escape. The problem intensifies in the middle atmosphere. Clouds reflect sunlight very effectively, but they also act like insulation. Each layer absorbs and re-emits infrared radiation, bouncing energy between layers like signals in a hall of mirrors. Thermal energy doesn't just get blocked, it is redirected downward. The thick lower atmosphere becomes a compression chamber, warming through both greenhouse absorption and physical pressure. Gas at high density resists cooling and radiates poorly. Venus becomes a heat reservoir that the sun simply continues to charge. The surface composition worsens the effect. Basalt absorbs visible light effectively. It warms and releases energy steadily. Without water or vegetation to moderate heat, the basalt radiates strongly in infrared, the worst possible wavelength for retention. The planet behaves like a heating element that never shuts off. Another factor is time. Climate systems on Earth adjust through seasonal cycles and geological processes. Venus has neither. It rotates slowly, giving its days months of sunlight at a time. Heat accumulates, and night arrives too late to matter. The planet's crust does not recycle carbon dioxide or bury greenhouse gases. The cloud layers do not rain on the surface to cool it. Nothing resets. This is why Venus is not a world that occasionally overheats. It is a world locked in thermal imprisonment. The albedo is misleading. The brightness is not safety. It is camouflage. The clouds repel sunlight only to trap the heat that matters. A mirror on the outside, and a cage on the inside. Venus became the perfect demonstration that reflectivity alone cannot save a planet. What matters is what happens to the energy that makes it through. On Earth, heat is part of a cycle. On Venus, it is part of a trap that never opens. The electrical activity detected in the clouds, and why Venusian lightning behaves unlike Earth's. On Earth, lightning comes from storms, towering cumulonimbus clouds filled with ice crystals, updrafts, and turbulent air. Electrical charges build as particles collide, separate, and polarize. A flash of lightning is the release of that imbalance. But Venus is different. It has no giant water clouds, no seasonal thunderstorms, no towering vertical columns, and yet, somewhere within its acidic atmosphere, electricity crackles. Lightning exists without the storms that normally create it. The first hints of Venusian lightning came from the Venera probes. Their microphones detected bursts of static that resembled electrical discharges. But the detections were limited. The microphones lasted minutes. When NASA's Pioneer Venus mission orbited the planet, it also picked up radio emissions. Short, sharp pulses, consistent with lightning. These signals repeated enough that they could not be dismissed as instrument noise. Something in the clouds was releasing energy. Understanding the mechanism requires abandoning Earth-based intuition. Venus's clouds are not water vapor suspended in cooling air. They are dense layers of sulfuric acid droplets, dust-like particles, and suspended aerosols. Within this mixture, collisions between droplets generate charge, just as rubbing two materials together can build static. But on Venus, the collisions happen in extreme conditions: high density, high temperature, and constant horizontal winds. Instead of climbing through a storm, particles slide sideways, colliding along enormous atmospheric rivers that circle the planet. Laboratory experiments show sulfuric acid droplets can hold charge differently from water droplets. When they collide and separate, they accumulate static more efficiently. At scale, this may allow significant electrical buildup without dramatic vertical movement. The clouds do not need towering heights to polarize. They only require time and motion, both of which Venus has in abundance. Then there is the superrotation. Winds in the upper atmosphere sweep around the planet at hundreds of kilometers per hour. These winds shear the cloud layers, grinding droplets against each other continuously. The speed difference between layers acts like a generator. Instead of one storm cell forming at a time, every cloud on the planet becomes a slow electrical factory. Lightning may not originate from isolated events. It may be a planetary background process. Some spacecraft observations suggest the discharges are weaker and longer lasting than Earth's lightning. They may resemble electrical arcs or sheet lightning, broad illuminations rather than thin bolts. The exact nature is still debated. Optical flashes are difficult to observe because the clouds never clear, and sunlight scatters inside them. So the search for lightning relies on indirect signatures: ultraviolet flashes, radio bursts, and electromagnetic spikes. The Japanese Akatsuki orbiter attempted to detect optical lightning in the infrared and ultraviolet. Results were inconclusive. Some frames showed faint glows in the cloud deck, but they were transient and unconfirmed. Other instruments recorded radio disturbances that matched lightning-like signatures. These findings suggest lightning is present, but not constant, and not identical to the storms we know. It may spark within specific cloud bands, triggered by thermal gradients or wave structures moving through the atmosphere. The absence of convection-driven thunderstorms is part of what makes Venusian lightning so strange. On Earth, lightning is a symptom of weather. On Venus, it may be a symptom of chemistry. Sulfuric acid droplets, mineral dust, photochemical particles, and metallic traces from volcanic eruptions could create charge separation purely through friction. No towering storm cells required, just endless atmospheric motion. One more mystery complicates the picture. Venus's surface emits occasional weak bursts of radiostatic. Some scientists suspect volcanic lightning, similar to the sparks seen in volcanic ash plumes on Earth. If active eruptions occur, ash particles rubbing together could produce local electrical activity. This would not require clouds at all, just hot gases rising through the near-surface atmosphere. The evidence is unclear, but it reinforces a theme. Electricity on Venus does not follow terrestrial logic. Lightning on Venus reminds us that atmospheric physics adapts to its environment. The same fundamental forces, charge, motion, collision, play out differently under different pressures and chemistries. The result is a world where electricity flickers in clouds without storms, where discharges whisper instead of roar, and where lightning may be a constant background murmur in a sky of acid and wind. The engineering ideas to cool Venus, and why everyone collapses under energy, chemistry, and physics. The concept of terraforming Venus sounds simple in conversations. Lower the temperature, thin the atmosphere, and maybe add oceans. Venus is not mildly hostile. It is locked into conditions produced by billions of years of runaway greenhouse chemistry. Every proposed cure immediately collides with a barrier: how much energy the planet stores, how much gas the atmosphere holds, and how fast fundamental physics pushes back. One of the earliest ideas was sunlight reduction. If Venus overheated because of the sun, perhaps shielding it would allow cooling. A giant reflective structure placed between Venus and the sun could decrease incoming radiation, but the size required is staggering. A shield would need to be tens of thousands of kilometers wide and constantly aligned to block sunlight. The force of solar pressure alone would push it out of position. Even if you solved that, cooling the planet would take centuries. Venus would radiate heat slowly, because its thick atmosphere traps energy like layers of insulation. The lower atmosphere would remain hot long after the clouds cooled. Another proposal was to chemically alter the air. Carbon dioxide is the primary driver of the planet's greenhouse effect, so maybe turning it into carbonates or solid minerals could help. On Earth, bacteria, oceans, and rock cycles perform this work naturally. On Venus, there is no water and no biological system to assist. Engineers imagined injecting magnesium or calcium compounds into the atmosphere, forcing CO2 to bind and fall as rock. The problem is scale. The mass of Venus's atmosphere is more than 90 times greater than Earth's. Converting even a fraction would require more material than human civilization could launch in thousands of years. Then came colder ideas: import hydrogen. If hydrogen were introduced, it could react with the carbon dioxide to form graphite and water. It sounds elegant until you run the calculation. To create oceans comparable to Earth's, you would need to deliver hydrogen equivalent to the mass of a small moon. That hydrogen would have to be mined from gas giants or icy Kuiper belt objects, transported across the solar system, and injected into an atmosphere that breaks apart water molecules. Even if you succeeded, Venus's heat and lack of magnetic protection would still strip hydrogen away over time. Engineers then looked upward. Maybe the problem wasn't chemistry, it was clouds. Venus's clouds block visible light but retain heat. If the cloud deck could be seeded to reflect more radiation or rain out corrosive compounds, temperatures might stabilize. But no seed material survives the environment. Sulfuric acid dissolves or corrodes everything, and rain never reaches the ground. Any artificial particle introduced to the clouds would undergo the same fate: chemical breakdown or re-evaporation. Some proposed a more drastic approach: strip the atmosphere entirely, remove the carbon dioxide directly, but the energy needed to do so is impossible to imagine. The gravitational binding energy of Venus's atmosphere is beyond any known technology. You would need to accelerate gas into escape velocity, over 10 kilometers per second, and do so continuously for millions of years. Every method of extraction becomes impractical once you confront the actual numbers. There is also the problem no proposal solves: geology. Even if you manage to cool Venus and remove greenhouse gases, the planet's interior would continue releasing CO2. Without plate tectonics and oceans, volcanic resurfacing would refill the atmosphere. Terraforming would not be a one-time project. It would be maintenance forever, against a world that continually tries to revert to its original state. Terraforming Venus is appealing because its size and gravity resemble Earth's. But the similarities end there. Every system on the planet, heat, chemistry, rotation, atmosphere, works against stability. What makes the idea impossible is not lack of imagination, but the rules of physics. Venus does not respond gently to change. It resists it. High eccentricity orbits, slow rotation, and the gravitational interactions that shape Venus's climate. At first glance, Venus has a nearly circular orbit and sits well within the stable inner solar system. Its path around the Sun is smoother than Earth's and more regular than Mars's. Nothing about its trajectory would suggest a world of extreme conditions, but when you expand your view beyond the orbit itself and consider the planet's rotation, tidal forces, axial tilt, and interactions with the Sun, you begin to understand how a seemingly gentle orbit produces a climate unlike anything known. The first anomaly is rotation. Venus spins backward and spins slowly, so slowly that a single day lasts longer than a Venusian year. The Sun rises in the west and sets in the east, moving at a pace that can take months. That rotation rate dictates how the planet distributes heat. Instead of day-night cycles refreshing the air, heat accumulates in long arcs of sunlight. On Earth, night allows the surface to cool. On Venus, night arrives too late to matter. The planet is slow enough that thermal energy becomes part of the climate, not a daily fluctuation. Then there is axial tilt. Venus has almost none. Where Earth tilts 23.5 degrees and gains seasons, Venus inclines at less than 3 degrees. Its poles do not lean toward or away from the Sun. There is no winter and no summer. The heat distribution is remarkably even. Clouds near the equator are not fundamentally warmer than those near the poles. Without seasonal variation, the atmosphere never resets. It becomes a global machine driven by constant solar input rather than periodic change. Gravitational forces complicate everything further. Venus is constantly interacting with the Sun, Earth, and even Jupiter. These gravitational influences nudge the planet's orbit ever so slightly over long periods of time. Though the orbit looks circular, it changes subtly. Astronomers call this secular evolution. slow adjustments to a planet's orbital shape and tilt caused by other bodies. Venus's path drifts. Its rotation synchronizes with solar tides, and the atmosphere responds on timescales of thousands or millions of years. Tidal locking is often discussed in the context of moons and exoplanets, but Venus demonstrates a different version. The Sun exerts tidal forces on the Venusian atmosphere and crust. These forces are not strong enough to freeze rotation, but strong enough to slow it. Over billions of years, solar tides drained rotational energy from the planet. This may be why the rotation is so slow today. The atmosphere itself participates in this braking process. When sunlight heats the clouds unevenly, atmospheric tides form. Those tides push against planetary rotation like friction against a wheel. Some scientists have suggested that Venus may once have rotated much faster. Over time, gravitational torques and atmospheric drag may have reversed its spin entirely. If so, climate is not the cause of the slow rotation, it is the consequence of it. Once rotation slowed, heat distribution became less dynamic. The atmosphere thickened, more water vapor rose, the greenhouse intensified, and the cascade that destroyed Venus's oceans accelerated. Orbital resonances provide another piece of the puzzle. Venus and Earth occasionally drift into weak gravitational rhythms. A pattern emerges. Every time Venus completes 8 orbits, Earth completes approximately 13. This resonance doesn't make Venus unstable, but it does affect the planet's relative positions. Long-term gravitational interactions may contribute to subtle changes in Venus's spin and axial alignment. We tend to think of orbit and climate separately. Orbit determines how much sunlight a planet receives. Climate is what the planet does with it. But on Venus, the two are inseparable. The slow spin traps heat. The lack of seasons leaves no escape valve. Solar tides amplify atmospheric circulation. The orbit may look calm, but the energy moving through the system is intense, constant, and directionally focused. If you stood in the upper clouds and watched the sun creep across the sky, you would feel the planet's inertia. Nothing rushes, nothing cools. Days are drawn-out exposures. Nights are brief intermissions. In that rhythm, Venus has no room to reset. The orbit feeds the climate. The rotation seals it. Venus is the only world in the solar system where a nearly perfect orbit leads to a perfect catastrophe. How Venus challenges assumptions about climate stability and the boundary between habitability and collapse. For decades, textbooks described Venus as Earth's sister, a planet that only went wrong because it sat slightly closer to the Sun. That description is comforting because it frames catastrophe as distance, a matter of luck, not consequence. But science tells a different story. Venus did not simply cross a line, it fell through a series of feedbacks. It is a planet that shows how fast a world can change when a climate system slips beyond balance, and how little is required to trigger irreversible instability. The process began gradually. Venus warmed, oceans evaporated, and water vapor collected in the atmosphere. That vapor trapped heat, which produced more evaporation. The loop accelerated. Eventually, the upper atmosphere split apart those water molecules, sending hydrogen into space and binding oxygen to the surface. By the time the ocean disappeared, the planet had already baked itself into a new equilibrium. Carbon dioxide filled the atmosphere, and the greenhouse effect deepened until the surface temperature reached nearly 500 degrees Celsius. The unsettling lesson is that Venus never needed a single dramatic disaster to become what it is. No comet strike, no sudden volcanic winter, no continent-destroying event. All that happened was that heat overwhelmed the planet's ability to cool. That is what makes Venus such a powerful warning. Collapse can be incremental. A civilization will notice a volcano or an asteroid. It may never notice the point where evaporation becomes permanent. Earth has stabilizing mechanisms that Venus lacks: plate tectonics, oceans, biological carbon sequestration. But those systems are delicate. Plate tectonics requires internal heat flow and active mantle convection. Oceans require temperature gradients that allow rainfall and evaporation to remain in balance. Life itself only moderates CO2 because it inhabits environments within a narrow thermal range. If those stabilizers weaken, the feedback loops strengthen. And on climate scales, feedbacks do not argue or negotiate. They compound. When scientists model early Venus, many scenarios show an era of habitability. Some models produce clouds, rainfall, even shallow seas. In these simulations, Venus is Earth-like not because it imitates Earth's biology, but because physical laws allow it. The transformation into a furnace was not inevitable. It was triggered. Small changes in solar heating, atmospheric composition, and rotational effects accumulated until the climate crossed a threshold it could not retreat from. That threshold has a name: the runaway greenhouse. It is a boundary where the atmosphere traps more heat than the planet can radiate. Once crossed, the cycle accelerates regardless of external input. Venus illustrates this perfectly. The Sun became only modestly brighter over billions of years, but the planet's response grew exponential. Heat created vapor, vapor trapped more heat, and the planet's interior began contributing as volcanism released additional CO2. The surface registered the final result, not the process. Some dismiss Venus as an outlier. They point to its slow rotation, its dense atmosphere, its lack of magnetic field. Earth could never become Venus, they say, because we are different. But the point is not that Earth will turn into a furnace with 92 bar pressure and acid clouds. The point is that planets do not drift gently into extremes. They plunge. Once feedback loops dominate, each degree of warming yields more warming. Complex systems collapse like dominoes, not like a thermostat. Venus forces us to rethink what climate stability means. It teaches that habitability is not a permanent state but a temporary balance. It shows that a planet can be born suitable for oceans and end as a desert of basalt and crushed air. It reminds us that physical laws do not care about the history of a planet or the life that may have once existed there. They only care about energy, chemistry, and equilibrium. The warning Venus offers is not about distance. It is about inertia. A planet does not need to move closer to the Sun to fail. It only needs to lose its ability to cool. The scientific lessons encoded in its atmosphere, geology, and silence, and why ignoring them is dangerous. Venus does not speak in language, images, or memory. It speaks in physics. It speaks in pressure, temperature, and chemical residue. It speaks through stone that has been melted and remelted. It speaks through clouds that swallow sunlight and reflect it back into space while trapping heat beneath. Every part of the planet is a message from the past, preserved not in fossils or oceans, but in a frozen equilibrium of catastrophe. Its atmosphere is the first lesson. Venus is not a world slowly warming or gradually drifting toward instability. It is a world that crossed a boundary and never returned. The atmosphere is heavy, not because it was always this way, but because there was no mechanism to stop carbon dioxide from accumulating. Water once acted as a thermostat, moderating Earth-like climates until it evaporated and was lost. What remains is a chemical tomb. 96% carbon dioxide, precision engineered by time to hold heat indefinitely. The silence of Venus is not the absence of weather. It is the absence of moderation. Geology is the second lesson. Earth records its history in strata, fossils, and sediments. Venus erases its own history. That erasure is not a metaphor. It is literal. The planet periodically floods itself with lava, resurfacing vast areas in single episodes. Entire continents disappear under basalt plains. Craters that could mark past eras are paved over. Tesserae, those fractured highlands, are all that survive the rewriting. They are the only places where Venus silently admits that it was different once. The rest of the planet insists that time began somewhere far more recent. Its rotation is the third lesson. Civilizations on Earth define time by sunrise and sunset, but Venus treats rotation as an afterthought. Days stretch longer than years. Heat builds across months, not hours. The planet's slow spin robs it of thermal escape, trapping temperatures at the surface that match molten metal. If Venus could speak, it would explain that climate is not just about the energy received, It is about how long energy stays. Then there is the absence of a magnetic shield. Earth protects its atmosphere with a dynamo hidden in its core. Venus does not. The solar wind tears away what little hydrogen remains, stripping the possibility of water molecule by molecule. If the planet could tell us anything, it might whisper this: never rely on luck to maintain stability. A magnetic field is not guaranteed. A temperate climate is not permanent. A planet is not safe because it once was. From orbit, Venus looks calm, smooth, white, featureless. Early astronomers imagined oceans beneath the clouds. The truth was the opposite. The calm is camouflage. Underneath lies pressure dense enough to crush steel and temperatures that sterilize everything. We often assume danger is dramatic: storms, eruptions, earthquakes. Venus teaches that danger can be uniform, constant, and built into the air itself. The silence of Venus is not emptiness, it is consequence. The planet does not rage, or scream, or explode. It simply exists in a steady state of ruin, a warning encoded in equilibrium. Every probe that landed there died not because of an event, but because Venus is the event. The failures are not tragedies, they are translations. If Venus could speak, it would not lecture or comfort. It would not threaten. It would simply describe the laws of physics that shaped it. How heat accumulates when nothing removes it. How atmospheres evolve when unregulated. How oceans vanish without protection. How slowly a planet can slide into disaster without a single dramatic moment. We are fortunate that Earth is not Venus, but that fortune came from balance, not inevitability. Venus is the reminder that worlds do not fall apart instantly. They drift, then accelerate, then lock in their fate. And once they do, silence is the only story left. Venus is not just another planet in the night sky. It is a mirror turned toward us, showing what happens when a world crosses the threshold between balance and collapse. We traveled through its clouds, where sunlight never reaches the ground. We explored its fractured highlands, its lava plains, and the scars of resurfacing that wiped away entire geological eras. We followed hydrogen, escaping into space, saw a magnetic field that never formed, and listened as probes descended into a furnace they could not survive. Along the way, Venus taught us that planets do not break suddenly. They change slowly, then all at once, until their histories are frozen in stone and atmosphere. Earth and Venus began as siblings, equal in mass, similar in composition, born from the same cosmic dust. One stabilized, nurtured oceans, and fostered life. The other drifted just far enough into sunlight, lost its water molecule by molecule, and sealed itself under pressure and heat. The lesson is not fear. It is humility. Venus reminds us that climate is a balance, not a guarantee. That habitability is not a permanent gift. That the universe rewards stability only as long as physics allows it. We do not preserve our world because it is fragile. We preserve it because the alternative is certain. As you prepare for rest, take a moment to be grateful for the quiet air around you, the oceans that breathe with the planet, and the atmosphere that protects you from space. They are the rare conditions that make life possible. Close your eyes. Let the noise fade. Sleep well